observatory and the EWB telescope had its 50th anniversary. Of course, the observatory was founded as a home for this telescope. It was donated by Edith Winstone Blackwell. And at that time, Grant was aware there were funds sitting around for the maintenance of the dome and the telescope that weren't really being used for anything, and presented a proposal to the trustees that they do something about spending some money on the telescope, and came up with this project. Now that he knows what was involved, whether he would still agree with that. So over to Grant and Steve, who are going to talk about a bit of the background and the project. Thanks.
Okay, thanks. I'm just going to give an intro, if you like, to the main event that Steve will deal with. Just to talk about the telescope, how it came to be here, what it's been used for, and what it probably could be used for. So this is the key thing here. You've probably all seen the Zeiss telescope, I presume, but it's basically a manual push-to telescope. You can push it for things, and that makes it slow to find things, and if things are hard to find, you can spend all night trying to find them. So, that's not a situation you want to continue. But so a remotely operatable telescope, like a research telescope, will can just say, go to this object, and it's there in 20 seconds, and any story using it. So that's the sort of aim for it. Otherwise, the telescope would become completely obsolete in time. So this is the Type 5. This is the guys that sort of did the work. Everyone's brought a lot to the table. This is really great fun working. We're still working together, still with friends, which is great. Right, so I mean the original story here came in the 1950s. The society was wanting to get an observatory, because this, until 1950, was the society's observatory in Simon Street, just near south, just on the harbour side of St Paul's Church, where the underpass goes under now. This field is now gone, but it's near the School of Architecture, that sort of general area. And that was there for like sort of 40 years on that site, not quite 40, maybe 30, and it housed that telescope, which is that telescope. So that telescope was used by the society. It's an 1859 vintage H. Jones refractor, and brought to New Zealand, I think, for the 1874 Transit of Venus. So basically the society from 1950 didn't have an observatory, and it set about all sorts of fundraising. Every time there was an Easter show on or something, they'd drag along telescopes, and people paid sort of sixpence to look through this telescope, and they gradually accumulated a little bit of money over time. But their vision was to get a new observatory. By 1956, Edith Winstone Blackwell, who was sort of a wealthy elderly lady, very strong interest in astronomy and other things. She offered to donate £7,000, which was an enormous amount of money in the 1950s, for the purpose of getting a telescope. And so this caused the Auckland Observatory and Planetarium Trust to form. So the society decided, well, this is way beyond us, so we'll form a trust board and get some heavy hitters on board that can drive this project. And that was the origin of the Auckland Observatory Planetarium Trust, which still exists today, in which we elect trustees to all part. And the society had by that time collected £3,500, which was pretty damn good. I mean, so that got tossed into the pot, and then the trust board set out looking for a telescope. They guessed about 20 inch aperture, which at that time was a big telescope, bigger than anything in the country. So that was what they were looking for, and after they got quotes from different people, but they eventually settled on the proposal from Carl Zeiss in Germany, which was East Germany in those days. Oh, that was one of the concept drawings of the observatory they came to. That was £250,000. So it didn't go very far. This is the original quote that Zeiss put in. You can see the detail, I don't know the details, but basically the telescope itself, £7,263. The thing they call Newtonian equipment was effectively what we would call a photoreducer. The telescope down to a Newtonian telescope like F7 for photography. So that's what that was, and that added a fair price to the very expensive, if you work out the variations, the very expensive field flattener and photo reducer. And the dome itself, which we've got, and that was £3,200 effectively. So that was done in 1960, and then there's a whole bunch of correspondence in the records of Zeiss leaking for the next 5 years saying you haven't placed the order yet, you're going to have to put the price up. And so finally, they did hold that price, but eventually that telescope was bought for about that price. And this is what it looked like before they shipped it from the factory. So it was a classical Cassegrain, 50 centimetre, 20 inch, near enough. The primary mirror F5, and for Cassegrains, F13.3 is very short. Typically the F16 would be a more typical Cassegrain, maybe F18, and the short one would be F15. So this is actually the shortest Cassegrain that I've come across. So a focal length of 6.65 metres. The reason for that was that the specifications, people wanted to do astrophotography with plate cameras. So to do, and they wanted to get like a Newtonian telescope, F7 or something like that. So in order to get that F7 with that focal reducer, you had to reduce the focal ratio down to F13.3. They included the refractor, which is the finder, 115mm, and on the other side of the telescope there was a 150mm Cassegrain guide telescope for photography, which effectively never got used. It's not on the telescope anymore. And there were various extra bits and pieces here. The feeler micrometer was for measuring the separation of double stars, which nobody ever used. The quarter-inch plate camera never got used, and this, because that never got used, that never got used. So all of those extras never got used.
What does Cassegrain mean?
Cassegrain means a optical system. Optical system designed by, invented by a Frenchman called Cassegrain, something like that in French. And so,
middle button.
Oh, thank you. Yeah, so in here, this is a reflecting telescope. So in here, there's a parabolic mirror with a shape, with a dish mirror like a telescope. Up here, you've got another mirror. So the light comes down through the telescope, hits this mirror at the bottom, bounces up to the secondary mirror, and it comes back down through a hole in the primary mirror and comes back here. So there are variants of that. There's a number of variants on that general idea, but that was invented by a Frenchman who was competed with Isaac Newton. Newton invented the Newtonian telescope, and Cassegrain invented this one, and today the Cassegrain is the most common. And this one on the side here, the sort of 6-inch one, is also Cassegrain. Big heavy foot here, that's under the floor, so we don't see that up in the dome. Drive motor, basically all the bits and pieces. That's the power supply that's on the roof, on the wall. So it arrived in 1966, late 1966. It was installed by Kurt Gottlieb from Mount Stromlo Observatory. He happened to be having his holiday over here, and the director of the observatory was Kiwi, and I'll say, I've got Kurt over here, why don't you grab him and get him to have a working holiday. So he worked during his holiday and did the assembly, which was great. And Trevor Roundway, a society member, assisted him, and Trevor was responsible. He did the polar alignment of the mount, and then that's perfect. It's been changed. So these are just some of the instruments. That's the instrument box. The box, we no longer have all the stuff. It just, for some reason, just went all over the place. We've still got the focal reducer, that's that thing there. We've got the camera. The turret eyepiece we did use, this part here, which is just 5 eyepieces on the turret, and this is the micrometer. So most of the stuff, the accessories never got used. So this is just the final, putting final touches to the building. This is building the, well, this is where the telescope is. This is the dome. This guy's doing the block walls and all that other stuff. So this is Kurt Gottlieb here, assembling the telescope. Brigadier Sir Bernard Ferguson, the Governor General. Lawrence D. Nathan, Chairman of the Trust Board, and this is Kurt Gottlieb here. Ron McIntosh, who was sort of a very well-known local astronomer, used to run the planetarium at the museum. Knew sort of that era, he was the old guy that used to do that. Did it pretty well. And this is Arthur Partridge, who's president all through the 1960s and one of the trustees. So the telescope soon got into scientific use, and in 1969 this instrument was made to go on the back, which is the photoelectric photometer, which has got a photosensitive cell in here, so when the light comes down this produces a signal. It's very sensitive and you can measure the brightness of stars very accurately with it. And this is all a range of things that were done with it, with that instrument over a period of 30 odd years. And only at the tail end here, after we were moving to CCD cameras, that with the Zeiss, some of this stuff started being done. Ian Griffin from, probably heard of Ian Griffin from the Otago Museum, very prominent in promoting astronomy. He was director here for about 2 years, and so he did spent a lot of time looking for asteroids, found 3. So spent hundreds, thousands of hours using that particular instrument. In the 1960s, they added an electric motor on the top here, so this is a secondary mirror. That's an electric motor, which is a motor from a Volkswagen and White motor actually. And Harry Williams, who was curator of instruments, was very creative guy for using cheap junk when we needed it, and so he built this electric motor on the top of it, move the secondary backwards and forwards, and when you do that, you can use that to focus the telescope. So we might one day look at putting something else back on the top here to move the secondary mirror backwards and forwards. It is convenient to have it. We took it off when we did the refurbishment. This is Pam Dale, who was the first manager of the observatory, appointed during the Halley comet year, because that was going to be a very busy year, a lot of public stuff, but Halley was a bit of a flop. That's a little cassegrain with the cover on. Hardly ever got used. It's just packed away at the moment. So the next sort of part of the story was in 2001, the Edith Winstone Blackwell Trust that was set up to distribute funds left over from Edith Winstone Blackwell's estate. The money we got originally was when she was alive and was in the will, and then she set up a trust to look after all the rest of the money, which was very substantial, and she was the trust was a major supporter of stuff. It funded a lot of like the maritime, the Lee Research Station, the University of Auckland Research Station, Marine Research Station. A couple of million probably went into that. Anyway, they called us up and said they wanted to give us $250,000 to the ongoing care of the Zeiss telescope, which was a wonderful surprise. The trust board invested those funds in a special fund so they wouldn't get messed up with all the observatory's money. It's used for other things. And basically the interest from that money would be used to maintain the telescope in the future. So that was cool. So the first overhaul that we did of the telescope was basically Mark Boss and I took the whole thing apart, and Paul Taylor's name. Wonderful photo, Paul. My favourite, that's what the light looks like. Even with the dome lights on, it's stunning. You know, John, people hate seeing me. Yeah, so Mark and I took this all apart. All the stuff that needed to be painted that we could move away did go away. The outer shutters of the dome were taken away to fix rust. The mount was all repainted. Every little screw and fitting here, the nickel plating had to be redone. It was deteriorating. It was a very picky little job. The interior was replaced, the flooring was replaced, and new furniture was put in. So that was a major job. But the telescope looked great after that time.
What is nickel plating?
Nickel is just putting a nickel coating on metal. So instead of putting steel screws in, you nickel plate them so they don't rust. But Zeiss's ones are all nickel plated, so we wanted to keep it looking the same.
All the shiny silver screws.
This looks like a dull silver colour. You can see them up there on the telescope. All these fittings here are nickel plated, pretty much.
Is nickel an element?
Yes, it's a nickel. It's like you could coat things in other things like gold, silver, nickel. Nickel seems like a better choice. So these are just various photos just showing the telescope. But around that time, it looked a lot more like it. I remembered it when I was young. when it was new. These are all nickel plated, for example. And so all that has gone all right, horrible. It looked much nicer once it was finished. So the telescope was back pretty much to the way it was when it arrived. The only sort of mod we did of one time we did the transit of Mercury, I think it was, and we had this simple little refractor stuck on the side temporarily with a steel bar, which never got taken off. Transit's been taken out now. But that's where it was, and that's the Zeiss drive. Anyone up there will know what the Zeiss, the clock drive sounded like, click, click, cling. Sometimes drives you nuts after a while. It doesn't do that anymore, it's taken away. But it was very, very reliable. So the next change was in 2012, was for the transit of Venus. We decided to dip into the Edith Winster and Blackwell interest money that had accumulated and buy this 6-inch lunt H-alpha telescope, which at that stage, there was only one other in the country, so it was his first equal in size. It was one Spottani. That was used to look at the transit of Venus, and Sean Fletcher, did a fantastic job at very short notice, grabbing the images off the little camera we had on this, and he very cleverly worked out how to process them so they looked just fantastic, and they were going up onto the website live as the event went on. Unfortunately, we got clouded out, so we didn't get the whole event in Auckland. But it's got a lot of potential, and school kids love looking through that telescope. That's something that educators do during the day. They take the kids up to the dome. But one thing that we learned, and Tim and I in particular were using this telescope, it's a research telescope in the smaller dome. So this is a bisque mount here, and it's really, really great mount, electronics and control systems and very good gears. So when we control this completely by computer, we don't have to move the telescope, touch it at all, and one of the main advantages of this sort of technology is that you get really good pointing. So if we want to slew somewhere to the point of a star, then the error is plus or minus 10 arc seconds typically on our slews. So anywhere you slew to, whatever you want is going to be in the middle of your field of view, smack in there. So that's to give you some idea. I think that is Jupiter's around about 40 arc seconds across, so 75% of our slews land in that circle. And 95% of the land would hit, planet Jupiter if you slew there, it would be on the centre of the crosshairs. So it's phenomenally good. It takes 30 seconds at the most to get there by the time it swings across the sky and you target things. So there's no time spent looking for things with computer control of that quality. So basically the thing about BISC is they also provide this, which has been sort of drooling over for a long time, large telescope upgrade kit, and that they sell it, and it's the telescope up to 2 metres, for those is only half metre, so we knew that it would actually drive the Zeiss around perfectly well. The trouble is it was $10,000 US, so we hadn't jumped in and done anything about it. Until I got a call. And this might be the first time toilets have ever been discussed at this astronomical society meeting, but it turned out to be a rather important galvanising thing in our story. And I got a call from the observatory chief executive who knew that there was a pot of dough from the interest from the Edith Winster and Blackwell donation, which was something that accumulated at $100,000. I didn't realise it was quite that much. But he wanted to grab $70,000 to upgrade the toilets. Well, that's freaked me out. Fortunately, there was a trust board meeting just about 10 days after that, so I had on the table there a concept plan of what we could do with the Zeiss, if we had that sort of budget, and convert the Zeiss into a computer-controlled telescope. So they were very positive about that. We can hear more about toilets. They still haven't been done, I might say, so hold your nose when you go. So there's a, anyway, so and then by January 23, I put down a sort of fairly detailed plan of what we could do with the Zeiss And that included, we needed a worm gear on the declination axis, because it didn't have one. It's got one on the right ascension, which is driven by that clock motor, and didn't have one on the other axis, which has still got to be pushed around by a computer. So the worm gear had to be purchased. The telescope control system for large telescopes, $5,000 US. That should be $10,000.
Unless you've got a cheap stash.
No, we didn't. No, sorry. Anyway, that's a small one. I beg your pardon, it should be $10,000 US.
I've got a screenshot of it.
Yeah, I thought there was something wrong with that. Anyway, and then we also ordered a large format CCD camera with a filter wheel and a temperature compensating focuser. So all of that kit came to about $25,000 US, which we ordered. And when the Zach gear came in, we had it on hand. We then set about to start the upgrade of the telescope. And that's what Steve's going to carry on.
Just to recall that one of the reasons it was delayed was because of Martian opposition was happening around.
Come into that.
Yeah.
Come on, Bill, come on.
Keep talking for 2 seconds while I switch sides.
Yeah, so are there any other questions about that? I mean, that's basically the...
Yes, I've got a
Yes.
question about the
Copyright.
Copyright.
Oh, sorry.
Initially, you said the funds were donated for the upgrade of the Zeiss telescope. So how come somebody was trying to draw funds from that?
Well, you might ask.
That is the question, yes.
The chief executive is no longer here. His role was to get out there in the community and sort of funding organisations and get funding. That's one of the things he does. But it's a lot easier just to look into our own bank account and say, oh, well, maybe we could grab this one. I wasn't impressed, but anyway, it doesn't matter. History down.
Did the board say that the money was not?
I don't know if he ever went to the board about it. He sounded me out, and I didn't want to. I wanted to have something on the table. If I hadn't had anything on the table, it might have come up, and they might have agreed to it, which I didn't want to see happen. It may or may not. I don't know. I didn't want to leave that option open. So this happened because it got. We've been thinking about it for a while, but it was that event that really sort of got something down in writing and serious talking to be done.
It made you move the motion at the meeting.
Maybe would argue that people who use the Zeiss telescope have to go for a week, so that probably the
That's right. Well, there you go. You see, I'm glad you're not on the trust board.
What happened to the guys scope and the motor?
Okay, the motor drivers, they're all packed away. Nothing to do with the Zeiss has ever been disposed of. Not, well, apart from that instrument box, which was wrecked in the 1980s. And the box, I think, actually was going to be thrown out, so Andrew Goodfellow took it and made it into a little toolbox for himself. Anyway, and there were filters and all sorts of things in that box, but they all just went, I don't know what happened in the 80s, other than here during that time. Sad thing. And the transformation system with that big focal reducer, it's obviously been dropped because it rattles rather alarmingly. We could send it down to Kiwistar Optics. They've offered to sort of have a look at it and sort of probably put it on a collimator and line it all up and fix it for us. We could look at that. Or we could just buy a modern one. I don't know what we do.
Okay, so this is where we started. So this was the Zeiss before we'd done any work to it. Still got an old battery light tacked to it because we wouldn't be able to change the bulbs. So as Grant was saying, the challenge is we wanted to make this robotic, and we needed to think about how we could do that. As Grant also mentioned, the RA axis, which is the polar axis, that we thought might not be too much of a challenge because there's a worm wheel in here and it was driven, so that clicking motor, that arm there, we went to a motor, that turned the wheel that's inside here to make it track, so that was turning the side you were right. So we were pretty confident, even though we hadn't pulled it apart, that side of it would be okay. The declination axis, of course, we want to make it go to, we need to make it point in both directions. There was no gear on here at all, so we knew that there was a pretty reasonable engineering challenge that we needed to do to make that work. What we also didn't know was what condition was this worm in here. So the telescope's 50 years old at this point. So there's a gear that's been turning on here every clear night for the last 50 years. We didn't know whether it was going to be worn. We didn't know how it was going to work at all. So step one was we were going to work out what gear we could get. As Grant said, we went to Mathis Instruments in California to get a bronze worm wheel. So this is from the website. And this is what we actually got. So it looks just as pretty in real life. And we got the worm pack as well, the worm wheel that goes with it, with all the adjusters on. And of course we needed to have motors and drives. So as Grant talked about the BISC telescope mount that we've got here, some of you have heard my talks before, well it's in this picture, which is me peering into the old BISC mount that used to be here when it was broken. One of the other stories that I've told about this is when this mount at this time, this is the one we have at Kumeu, this is 15 years old. This was well outside warranty and well outside software BISC wanting to look after us. We would expect wanting to look after us with this. When this mount failed, one of these boards in here actually failed, software BISC did come to the party and help us out with this 15-year-old mount and gave us an amazing deal on upgrading this mount with the very latest electronics. So this is the MKS 5000 drive system, all of the controls, all of the wiring. They even milled out a side plate for us to mount this all in. So software BISC is a really fantastic company to deal with. So we set about in my garage with the help of Tony, fitting all of this inside this mount and getting it working, and that's worked brilliantly ever since. As Grant also mentioned, this is the exact same drive electronics that are inside the research scope in the research dome here. So looking at this solution here, which is a TCS, BISC TCS system, so it's got the right price on it. This is off the website. It was pretty much a no-brainer. We did actually look at a couple of other options as well, but every time we talked about it, it was, why would we go to something that we don't know when we know the company, we know the equipment, and we've already retrofit a system with the same board, so definitely stick with what we know. So the next challenge is really how do we do it? Tony, who's here tonight, Tony Messenger, was our engineering brains behind this. And we started off with, wouldn't it be great if we could have some engineering drawings? So I just set off on the internet and found the website for the Carl Zeiss Jena archives and went digging through found a couple of photos on there. This one's the same as Grant's one. But these are off the Zeiss Jena archives site on the internet, and these are of our mount. And so we know that for sure because you just look at the angle here. So we know this is exact mount. And I thought this is really great because we now know what the number in the Carl Zeiss archives are of our mount. So that means we may be able to get actual engineering drawings. So I got in touch with the archives and we had a good conversation going backwards and forwards. But it turns out they really only digitized these kind of photos. But all the drawings, they were actually in a set of cabinets, and you can get them digitized, but you get them digitized at, I think it was about 35 to 40 euros per page. And there was about 80 pages there, and I said, well, can I get a thumbnail of them? He said, no, it's going to cost you the same thing to give you a thumbnail of the page as it is to going to be giving you the document. So it sort of started to look like it was going to be hundreds of dollars to actually get some drawings that may or may not be engineering drawings and may or may not be useful to help us in our endeavours. So we did what good Kiwis do, and we pulled it apart and had a look. So this is inside that RA axis that I pointed out before that's got the wheel in it. So this is the original worm wheel. This is the worm itself and its block. And that tube there is for grease. And that tube, there's a wheel on the bottom, and you tighten it up and grease on it. And we know that was working really well because I spent about 2 hours pulling grease out of this, and I was covered in 50-year-old ice cream. We didn't actually take any photos of what the worm looked like, unfortunately, when we took it out, but I do have one from the other angle. So from 4 of us taking photos throughout this process, not one of us took a photo of it when we took the worm wheel out, but I can prove that we did. So that's when we took it out. And that's the actual condition of the worm gear itself was amazing. We were really surprised. There was no noticeable wear on there. And the worm itself, Tony had it on a microscope, having a look at the actual teeth threads on the worm, and said it was really good. Turns out it wasn't perfectly circular, but it hadn't got significant wear. There was, I'll talk about that in a minute. So what we did is we made some measurements, or rather, Tony made some measurements, and some drawings about what we might want to do with it. So this is what the worm looks like. This is that block that you can see. This is the worm inside it. It had a sort of ball and socket joint on one side, and I can't remember what was on the other side. What was on the other side? It was the same. There's another ball and socket on the other side. Two different metals to have a low friction. Now they were a little worn. So our first theory was, this was our first idea, and that's because we needed to put a shaft on the end of it. The original, just rolling back a bit, the original worm gear had another worm gear underneath it, sort of a two-stage reduction, and that had a lot of backlash in it. So as you turn that, it wasn't going to be suitable for us driving it, and we'd had to drive it at a really high speed as well, so it wouldn't have lasted very long. So the idea was to put the gear wheel, the tooth belt wheel on the end of the shaft, and put a heat shrunk collar on there and some taper bearings. So this was our first design. Now, Tony's got a really amazing guy who works with him called Andreas, who can do anything with SolidWorks. So he turned all this into engineering drawings, and we ended up getting, that actually didn't come out too well when I copied and pasted onto here, we ended up getting some really good detailed engineering drawings made of this wormhole, which allowed us to start thinking about how we might do this exactly. So the first step we were going to do is get the motors working on the RA axis, because that was going to be the easy one. So having some 3D models allowed us to sort of look at our ideas, see whether it was going to work, and then move that forward. So Andreas then went and measured and created 3D models of how might we fit these motors. So he is one of the early ideas for how we might fit these motors. So this is the telescope, that big white cylinder that I pointed out earlier. This is where that worm was on the wheel, and then having that shaft come out there, and then the belts, and this was the motor that we received from Software Bisque out of that $10,000 pack. So this is everything in a line, but it did stick out the side quite a lot. If you look at this as the circle at the side of that. Now, one of the things we decided really early on is we really wanted to keep the Zeiss telescope looking more or less stock. We didn't want to make huge changes to it, and we didn't want to turn it into a high-tech robot-looking thing. So by having this arrangement, which is mechanically quite simple, and we kind of liked, we would have had to lose the pointer that goes around the side, which points to the circle, the same circle around the outside. So we go with the second solution, which was neater. It allowed us to keep the pointer there, and we put the motor on the back, and actually a third variant of that, which is more or less the same, but putting the motor out horizontally. And this was really good, but it came with a real negative that this plate here is that thick and it's cast iron. So we had to somehow make a big hole through that to get this big belt through. So some negatives there. Anyway, that was kind of the way we sort of wanted to go, and we got some more drawings done of what the whole assembly would look like with this, the original. So this was all original. This is the original worm block with the original worm in there, but modified to fit this gear. That's the motors we got from Bisque, and all this was going to be manufactured, and we were going to cut a hole through this. And this was actually, I know granted that we started in September last year, but all this is actually in April, May of 2018, April, May last year. And we got the go-ahead that we're going to stop using the Zeiss, and we were going to have the Zeiss out of action for between sort of about 4 to 6 weeks to do this part. Pull it apart, get this part off, and then get it working. Then this happened. So Mars happened. This is one of Sean's pictures, which I stole from Facebook. So we essentially got shut down for about 3 months. There was nothing we could do because the work that we really wanted to do, which was to start having a look at what was inside the declination axis. We'd had a look at the RA axis. We couldn't do that at all because in order to do that we had to take the telescope off. And that required a crane, and it wasn't going to be back in action. So we sat around just looking at all these fancy toys we had and things that we wanted to get done, and we couldn't really achieve anything for that time. But as it came to sort of about this time last year, actually it was late September, so it was coming up for this time last year, we finally got the go-ahead that the Zeiss was going to be taken away from public use, and we could So how do we do that? The steps were we're going to take the mirror out. Now this is this cradle is something that's been used for a few years now. I don't remember the history of it. Who built it?
2000 we had it made.
2000. So Mark, Boss, and Grant had this made to help get the back of the telescope where the mirror is off. So we had to get the mirror out. So you put that cradle there, which is on a hydraulic winch, and drop the mirror out. So pulling the mirror out of the scope, that's what it looks like, it's the cradle. We obviously had to take off all the accessories on the side, so the solar scope, this is the solar scope that Grant was talking about, and the finder, so they came off as well. And then all of the old wiring that was inside the telescope, so to take the telescope tube off itself, this is the wiring that was in there. So all for the lights, and I'm not sure why there are relays and resistors and capacitors and all sorts of things. I've never quite worked out what these are.
At the top of the drive.
Oh, part of this was for that drive motor, right? Okay, that makes sense. So we pulled all those out anyway, and you see that all of these wires were unceremoniously chopped because they weren't going back in there again. And also the wiring that was at the top. So this is the wiring that went all the way through the mount. This is the original 1950s big chunky German wiring. And eventually we got all of the parts off the telescope. So that's what it looks like stripped out. So there's no mirrors in there. There's no secondary mirror in there. We've got the wiring disconnected. The reason that this needs to be here is that once you take the mirror out, the counterweight is now too heavy. So if you don't have that prop there, the whole thing will rotate. And of course, we already taken out the worm drive here. So you can see there's a hole there. So there was nothing. It was freely rotating. So the telescope was ready to come off. Next step was to get the cranes in. So these guys from NZ Crane Hire quite like us now. It's a little bit different, lifting telescopes off mounts and things like that, rather than just lifting bricks up to a building site or something. So a quick 1-minute video of us actually taking the telescope off. Grant was the one that volunteered to stick his arm inside it as it came loose while it was swinging around. And one of the other things, because we disconnected the power at this stage, we'd also disconnected the power from the dome. Now, in order to get the telescope from where it was there to on the floor over here, the dome needed to be rotated. So you'll see that it is moving now, but that's because Grant was doing this by hand.
What's the weight of the telescope?
With the mirror and everything, it's about 500 kilos. So at that hand, it's probably about 300 as it is stripped between 2 and 300. The counterweight is just over 200.
Speaking of counterweights, how much did you have to, I presume you'll have to adjust the counterweight to get balance back after you down with all the other bits?
Well, yeah, I'll get to that. I'll talk about that. You'll see some of the work we did to work out how much it needed to change. So counterweight was a similar story. So again, Grant puts his life and limb on the edge. So you see that we've got yeah. So we didn't know how that was going to move. We didn't know how heavy that shaft was, and we had to unbolt it and just hope that this sling that these crane guys said is definitely going to be fine, it didn't just go tip and fall out, because Grant stood on a ladder there. He isn't just stood on the floor, and there's a few of us around it. So yeah, a fall from that height would have been not ideal. We discovered after we got that down and on the floor that there were 2 nickel-plated covers on there, and we unwound them, and I don't know if you can see them on any of these actually, but we unwound them and had a look, and they were threaded inside there, and then we realised that that's actually to screw in some eye bolts so that you can lift it. So we bought some of those. I've got a picture of those. There you go, there's the covers. underneath those covers is where you're supposed to put the bolts to lift it off. But again, we didn't have any engineering diagrams, we just learned as we went along. So with the scope off, we could have a look at what was under the scope. Now, the telescope had come off in 2003, so Grant had seen some of this before, but in terms of doing this retrofit, hard to say how you were going to do it. So we didn't know what we had in terms of where we could put this gear. We bought this 15-inch bronze gear from Mathis, and we didn't really know how we were going to attach it and what we were going to do. So this is what we found when we took the telescope off, all the wiring. So we decided we need to get the wiring out. This was how the wiring went through. This is where the counterweight was. So the wiring that we saw there went all the way down the middle of the counterweight of the declination shaft, the bit that turns, out the other end here, and then did a U-turn. That went all the way back down to the middle again. So, and that's actually quite a smart design because it means that as the telescope's turning, you've just got this sort of 2 metre long length of wire just able to twist gently rather than getting tangled up. So we pulled all the wiring out so that because we need to get that end off.